So, welcome to the Chemical Consultants Network a meeting. We are a nonprofit organization with several hundred consultants. We are chemists, chemical engineers, life scientists, and other interested scientists and engineers of other chemical allied disciplines. We hold monthly meetings on topics of interest to consultants to help start, practice, and enhance consulting opportunities. Our meetings cover common issues such as taxes, regulatory compliance, safety, technical developments in science and technology, such as we're going to see here tonight. Through our website, we provide platform to advise potential clients about our areas of expertise. CCN is supported in part by the Philadelphia section of the American Chemical Society and the American Institute of Chemical Engineers. So this is a very special group of people. We are happen to be actually the world's largest organizations of chemical consultants. So welcome all. Before I introduce Paul, there's one more thing that I'd like to talk to you about, and that is for those people who have introduced themselves and have not had a leadership position in our organization, please consider running for our for couple of the positions that are opened up. We have several positions that are open. One of them is going to be the president or the chair-elect for the next 2 years. Membership chair, marketing chair, and there's one more that I'm forgetting. But yeah, please, I'm going to be sending out an email or we're going to be sending out an email shortly to you. Please read it over and consider becoming a member of the steering committee. Thank you very much. Okay, so so finally we get to talk about Paul, and I am very happy that Paul is going to be presenting, not because he's a great guy, but because of the type of work that he's going to be presenting. Paul Fishbein is a graduate of Bronx High School of Science, and he has obtained his bachelor's in the chemistry from the University of Rochester, and his doctorate in organic chemistry or organic synthesis from University of California. Paul was also a postdoc at University of Houston, and then a postdoc fellow at Schering-Plough Pharmaceutical Company. Paul spent beginning of his career in the chemicals and pigments department of DuPont, and then most of his career was with Johnson Matthey Pharmaceutical Materials. He became a senior principal scientist, where in addition to being a project leader, he was in charge of kilogram scale GMP laboratory as well as all reference standard syntheses. Then Paul worked for an intellectual property prior art search firm and also at Keystone Research and Pharmaceutical Company as a senior research chemist and a patent liaison. In addition to this, he's also an adjunct professor at Rowan University, teaching a graduate course in process chemistry in the pharmaceutical industry. Paul holds several patents in drug substances syntheses and in fingernail coating formulations. Please welcome Paul Fishbein.
Hi, I assume everyone can hear me?
Yes, you can. We can hear you, Paul.
Good. Thank you so much for the opportunity to present this work to CCN. Peter, it is also a pleasant surprise to recognize a number of the people that are here, and I look forward to speaking with you. All right, well, why don't we go ahead and get to it? The title is self-explanatory, but if you don't know what statistical design of experiments are, basically it is a way of exploring the experimental space of a process. Could be a chemical reaction, could be something else. And it's very math intensive. You really can't do this by hand. You would really have to use a computer program. And my personal experience is that as user-friendly as they try to make them, you still have to have a pretty decent background in statistics in order to use it and make sense of it. Now, one of the drawbacks to using it is that you have to do all of the experiments that it suggests in that experimental space before you can make any conclusions. And that's really a drawback, because if you're under pressure, if your boss or your client is expecting you to get results more quickly than not, that could be a serious drawback. So there are ways of getting to an optimum that are fairly simple, that don't involve the use of advanced statistical knowledge. Having said that, nothing I'm going to talk about today, in addition, well, I'm not going to talk about it, to statistically designed experiments, should be construed as a replacement for what I call chemical intelligence. That could be engineering intelligence, business intelligence. Really, that's where you're going to make the biggest leaps in improving something. Continuous improvement type of things will get you so far, but it's really your experience, your intelligence, your learning, your education that will get you there. So I'll also sprinkle in some real life examples as we go through this. So let's start. All right, so the first thing I want to talk about is, what do I mean when I say an optimum, when you're optimizing something? And that, I mean, if it's, say, I'm going to use yield as a primary example because it's something that I'm most familiar with, the chemical yield of a reaction. Well, then it's easy. You just want to optimize the yield. But what happens if you want to optimize the yield, minimize the cost, maximize the throughput or space-time yield all at the same time? So what is that? What is the optimum? And then we'll go over the techniques to achieve this. So my definition of the optimum is, it's really a compromise. So let's look at this figure here. It is I wouldn't call it a typical uh, uh, response surface. You can see how it's not just a smooth, simple response. This is one made up of two factors or two variables, maybe temperature, maybe pH, maybe concentration. And this is the response. This could be anything. Let's, for the time being, just say that it's yield, where 100 is 100% yield. So you might be looking around, how do I get to this point? Well, here's a plateau. This is what we would call a local optimum. This over here is what we would call the global optimum. Now, there's something about all optima that is important, that it's not just a matter of getting to an optimum, the best possible, say, compromise, but it also makes everything more stable. If you think about it, as you get to the top of this curve, the global optimum, it looks like it's starting to flatten out a little bit. It's certainly not as steep as the sides. And that's really important, because if you're at an optimum, however you wish to define it, it's going to be a little bit more stable than if you are not at the optimum. And you can understand that if you make a little bit of change and you're not at the optimum and you're not on this plateau, say you're over here, a little bit of change in, as we're looking at it, factor X2 can result in a big change in the response because you're sliding downhill. But if you're at the optimum and you make a small change in factor X2, it really doesn't have that much of an impact. And that is the other reason for getting to an optimum. So it's not just, yes, it's, the best possible situation, but it's a more stable environment. Okay, so we talked about what an optimum is, but then how do we combine different outcomes into a single number, into a single expression? So we do that using something called a desirability function. And the desirability function, which is capital D, is made up of what I will call desirability factors. Those are small d. And mathematically, it's the factors, the product of the factors to the nth root of the number of factors. So if you had just two responses you're trying to optimize, you'd multiply them together, take the square root. If you have four, you'd multiply all four together and take the fourth root. Well, what does each one of these factors look like? It could look almost like anything, and this is totally up to you. The only thing that it has to do, there are just two requirements. One is that it's going to be normalized. So on the y-axis of all of these graphs, it goes from 0 to 1. On the x-axis, it's whatever you want it to be. If it's yield, maybe it goes from 0% to 100%. Or maybe it's, I don't know, throughput. It might go from 10 to 100. It's whatever you want that to be. It could be an impurity level as well. You go from no impurities to 0.5% impurities. And as far as what the shape of the graph of these looks like, it's totally up to you. The only other requirement is that for each response, so for each number on the x-axis, there can be only one number on the y-axis. So you can't have a curve loop back on itself. There has to be just one. So as an example, if you look at the third one down on the left, that might be impurities. So let's say that you have a specification in what you're making of not more than 0.2%. Above 0.2%, it's not a saleable product. You're going to have to rework it or reprocess it or burn it. And in pharmaceuticals, at least, you cannot blend it off. And in fact, if you're making something where you can blend it off, if you rely on that too much, you're going to end up with a whole bunch of batches that need to be blended off and nothing to blend them into. So it's really better to, the classic do it right the first time. So again, this third down on the left, we've got anything above, say, 0.2% is no good. That's a zero desirability factor. If you have no impurities at all, well, that gives you a 1. That's +1, right? That's perfect. No impurities. You could say that it doesn't really, there's not a big difference between having no impurities and, say, having 0.1% impurities, half of the specification. That's fine. There's no reason to have to continue to investigate, say, a reaction or a process, because once it's 1/2 of the specification, you're going to be safe. That gives you wiggle room. But once you get between 0.1 and 0.2, it becomes less desirable. You want that wiggle room. So that's why the line in that graph is sloping downward to the right before it basically goes straight down at 0.2, and above that, it's not acceptable. When I make these kind of graphs, I do them freehand. You could, I suppose, create a mathematical formula and say, let Excel do the calculation, but there's really no point to doing that. You instead can just use your hand, and I've used a French curve, and then you just read it off the graph. You get uh, a number for each one. Say this is yield. That's a silly thing to say, but let's just assume that this is yield, and maybe this is throughput, and this is impurity level, so forth and so on. They're all normalized to be between 0 and 1. You multiply them, and if you had 3, you take the cube root, and that is the number, the desirability function. That gives you an idea as to whether or not you're getting closer to your optimum. All right, so before finding the optimum, you have to reduce the noise. And this goes for whether we're going to use the techniques I'm going to talk about or statistical process control, or rather designed experiments, or any, just random looking around. It does not matter. If you have so much noise in your system, you're not going to know if a change that you made really has any impact. So you can use statistical process control techniques to follow it and try some things. Some design of experiment techniques are focused on reducing the noise. And as an example, let's say you were making some kind of electronic component and you're sampling it initially. This is where you are initially, and there's a lot of noise here. So you could make a change and you'll never know if it resulted in something significant, which is really what statistical process control is all about. You did something, the typical methods used to reduce noise, and now you've got the graph that's on the right where it's much less noisy. So if you do change something, you'll see if it really made a change or not, because it'll become significant versus your noise. So this is pretty important. So at this point, if you get nothing else out of what I'm saying, you know how you can take a bunch of different outputs, turn them into one quantifiable number, and you know that you need to reduce the noise of your system. All right, so we all learned in school that you hold everything, all the different variables and factors constant except for one, and then you vary that, and then you hold that one constant as well, and you only look at one more. That really doesn't work. Not when you have a system where the variables can interact. In statistical process, pardon me, I keep saying that. In designed experiment land, that would mean that the impact of a variable is very different depending on the levels of the other variable. So what we have here in this graph is a response surface. Now, you don't know what that surface looks like unless you go through all the statistical design, and then you have a decent idea of what it is. So you don't know what that is. All you know is if you change something, do you get a better result or not? And as far as how to interpret the response surface of what we're looking at, think of it as a topographic map if you've ever gone camping or hiking, and you're looking down from the top. Okay, so the middle here, that's where the optimum lies, and these are just ISO, I'll call them result lines that indicate how much less or the absolute amount away from the optimum is. So let's say we started here. All right, this is point A, and you decide to hold factor 2 constant, and you change factor x1, that's on the x-axis. So now you've arrived at B. Well, B is worse than A, so we don't want to go in that direction. So we keep going to the right. You try this point, it's better. Try this point, it's better. Try this point. I would argue that this unlabeled point is better than this one. The source that I got this from seems to think C is better than this unnamed point, but okay. Move a little bit more, now it's not as good. So, okay, for the sake of argument, we'll say that C is the best you could do. Now you're going to hold factor x1 constant and look at factor x2. That's the y-axis. All right. How big a step size do you take? Well, you don't know that when you're starting. So you're going to take a step size, one that you can actually perform. Maybe if it's temperature, maybe 5 degrees, maybe 10 degrees. We don't know. It's probably not going to be 1 degree if you're really going to start scaling this thing up. So you try point E. Well, that's not as good as point C. You try point D. That's not as good as point C. So you claim to be done, and the best you can get is point C. Well, that's ridiculous.
Why is it not as good?
I'm sorry? Okay. Here's where the optimum is. Maybe this is good enough, but remember, we're trying to get to as best as we can in as few steps as we can. So you've missed it. This is where at least it's somewhat close. Imagine if you started much further out. I would also point out that there is a time when one factor at a time will work, and that's when the response surface is a bullseye. Then it will work. I've never come across something like that before. They're always these curved planes that go up or down, side to side. If you have a response surface and you wouldn't know it at the time, that's a bullseye, yes, then this will work. But after that, or if it's in higher dimensions, a sphere in the middle of your experimental space. So, all right. So we've been talking about responses and methods in general. Let's talk about one that is useful for formulations. Also, the order of addition of, say, all the materials that go into it, or maybe the order of operations. Maybe you're working on something that's a little bit more mechanically inclined, and you have the possibility of doing all of the operations in a different order. So let's say you had 4 constituents. Does anybody know how many ways there are of taking 4 unique substituents, 4 at a time, in different ways? It turns out it would be
24.
right, 24 different ways of doing this. I don't want to spend my time looking at 24 different combinations. And it is my experience is that your manager or supervisor or the vice president or your client isn't going to be too inclined to run 24 different trials before you can say, this is the one. So there's a way of doing this that minimizes the number of trials. So let's say it's easier to just discuss this in terms of 4 different constituents. So this will be order of addition. We have A, B, C, and D. What you want to do is to keep the last constituent that you added always as the last one. I'm sorry. The initial trial of this is you're going to keep moving the last one to the front. So here's the second trial. You move D to the front. So now you have D, A, B, C. You move C to the front, B, C, D, A, B, and then finally you move B to the front. So these are 4 possibilities. If you moved A to the front, then you'd be back to where you started again. What this method does is it's looking for pairs of constituents that create an intermediate that you have to have present before you can do any of the subsequent steps. And that's done because you're breaking up every possible pair. All right. So let's say you do this and all of these give you the same result. Okay. They're all just as good as each other. Great. You're done. Stop. Yes, you could say I only did 4 and there were 24 different combinations, but it's pretty unlikely that you're going to find something beyond this. But for the sake of how this works, let's assume that this second one, that the second one is better than the other remaining 3. So now what you do is you fix C in place. C is always going to be at the end. And you do the same kind of operations, except now it's only to the first 3, D, A, and B. So here is C is at the end, and we've moved B to the beginning. All right. C is at the end. We moved A to the beginning. Those are the 3 possible combinations, because if I move D to the beginning, then I'm back to where I started. Again, you look at which is the best, number 2, number 5, or number 6. If the 2 new ones are worse than number 2, fine. Number 2 is your quote unquote optimum. If one of the new ones is an optimum, and again, for the sake of this presentation, let's assume that number 6 is better than everything so far. You hold D and C constant, right? Because you just explored these 3. D is now at the end, or is fixed, I should say. C is still at the end. And now you have just one more trial to try, and that's by switching A and B. And that's it. You've just done 7 different possible, I guess these are permutations, not combinations, as opposed to 24. If you want to do,
I have
I'm
a
sorry,
question.
sure.
What does it mean to switch the order of the variables?
It's okay. All
Each
right.
variable has a range, right?
Well, this would be addition of constituents. So say you're making, I don't know, a polymer. So you've got the monomer, you have I forgot the term already, the sort of preformed part of the polymer. You've got an activator. There's probably not a solvent, but maybe there is. So you've got 4 different things that you're throwing in there. What's the best order that you can put that in so you get your best results? And the same thing with operations. Maybe you have a micronization step. Maybe you have a sieving step. Maybe you have a drying step. Maybe you have, I don't know, a centrifugation step, actual sort of mechanical things. That's what these would represent. Does that answer your question?
Yeah, it does.
Okay. And I'm looking here. Yeah, you really don't have to totally randomize what's going on as long as you pick something to start with. You could argue that, yes, you're only looking at 7 instead of 24. But again, this is where your chemical intelligence, your engineering intelligence comes in. You're already having chosen something that you think is pretty good. There's reason for that first trial. If you are totally in the dark, then you're going to have to do a lot more. But you don't necessarily have to randomize this each time. Now, this is just 4 constituents. I've had situations where there are like 5, 7 of these things, and it became totally impractical to run all of it. So again,
Well, I've stopped listening to you. I've stopped hearing you. Is there any problem with the system?
Now I'm gonna check and see that
Paul,
he,
are you there?
now this is a meeting host. It says that
Yeah,
Paul
it's the meeting
still here,
host.
but I no longer,
He left though.
yeah, I suspect it.
Well, I think this is where the chemical design in terms of computation comes handy when you actually make a choice of which constituent to use in order, or with automation, we could do it parallelly technically. So run parallel computing, it's quite more sophisticated and would find a faster solution. But generally speaking, I don't know. Let's wait for Paul to come back.
I'm calling the speaker to make sure everything's okay.
All right.
Thanks, Joanne.
Please stand by. He's had an internet connection problem. He's gonna use a different connection and come back in. So
Excellent.
Well, I've been using a public connection, so that might be jeopardized, but I apologize for that.
Rado, did you want to say something about yourself? I don't think you introduced yourself.
Oh, that's right. Well, I've been working mainly into a computational part of chemical systems within nanobiospaces. So we try to understand better the factors and the outcomes of interference within so many variables that we try to deduce them in terms of like understanding further implications that may come into drug design, or especially considering the topic of interest like this lately has been mainly heterocyclic modifications and the issues with the RNA world. But in terms of what Paul has been talking about, when it comes down to computing a chemical synthesis, we do generally try to do inspire more into a biosynthetic pathways and learn a lot from nature. Some kind of an agreement due to lots of interference that are undesirable in terms of when well-trained organic synthesis people have not well analyzed or perceived the biosystems and vice versa, and therefore such interdisciplinary tendencies would be quite useful, I would say.
all right, I am back. Let me bring up this. Share screen. Sorry about that. My server has seen better days. All right, we are back. People can hear me?
Absolutely.
Okay, good. All right, sorry about that. All right, so one of the things you can do, which if you really have a limited amount of time and you can see that it's going to be a tremendous amount of work, is you can actually calculate what the chances are of your improving the process, which I think is kind of interesting. So the first thing you want to do is to run a bunch of random experiments. That's why I'm not too thrilled with this particular technique. It's somewheres between, oh, it's telling me I have an unstable connection. All right. It's telling me what you want to do is to run between 10 and 20 experiments. 13 is a good number. 10 doesn't give you the resolution that you might want, and 20 is unnecessary. It's too much. So, and when I say random, I really mean random. Use a random number generator to set your variables. Use a pair of dice if that's what you have to do. But it's really important that it be random. Don't try to outsmart the system. You get your results, and then you order the results from the lowest to the highest, and you assign them a rank, where the lowest is 1 and the best is, in this case, 13. You do this calculation. I'll show you what that ends up producing on the rank is from the order that you put it in, and n is the number of experiments. In our case, it's 13. And then that calculated number will equal to the probability that you can find something better than that particular result. All right, so let me show you here. So let's say you ran, these are the 13 experiments, and they were random. You put them into rank order from lowest to highest, 1 to 13. You do the calculation. Okay, so this tells me that after running 13 random experiments, the chances of my finding, and let's again use yield because it's simpler, this might be the desirability coefficient. I've only got a 7.2% probability of finding a yield greater than 69%. Well, let's say that you only ran, say, 5 experiments, or someone ran them for you, and then you were stopped. I don't want to keep doing this. The best that you got out of the 5, you'd have a 17% chance of finding something better. All right. If you can live with that, great, then only do 5, but you're not quite exploring as much as you need to. Again, the downside of this is that you're running some 13 experiments before you can say much. Otherwise, wherever you stop, the denominator is going to change, and that's going to increase the probability of your finding something greater, or I should say, yeah. Part of this also, remember I said that you're going to run random experiments in your experimental space. I cannot emphasize enough. And again, this is where your chemical engineering business experience comes into play. You do not run something that is potentially dangerous. Okay. This kind of thing, because you're running all over the experimental space, you're not going to want to do this in the plant. So they'll do this in a laboratory. But even then, you do want to be careful. Yes, you've got a hood sash down, and if something goes off, it's contained, but that's still pretty bad that you've destroyed property. And it's when I say your engineering intelligence, your chemical intelligence, I really do mean that. Let's say you're looking at just two variables, temperature and pressure. And you know that the equipment you're going to run it in can withstand a certain high temperature, and it can also withstand a certain high pressure. But when you put those two together, you're probably going to exceed what the capabilities of the equipment are. So you really need to think about this. It's good to get a second pair of eyes looking at this when you start to do something like this. But people have, when I get to the last method of doing this, have blown up a plant, or plants, I should say. It's happened more than once because they get so entranced with the technique that they forgot that they really have to spend a lot of time thinking about that experimental space and what are the limits of it. All right, so now we're going to move towards something that finds it. It's going to look around the experimental space. So again, define the experimental space. Please, please do this carefully. In this case, you run just 5 random experiments. And again, random. Do not worry about covering the entire space. If you are truly able to set your variables randomly, do so. Again, you can use something like a random number generator or dice or whatever works for you, a table of random numbers, use that. You run your experiments. Let's say, for the sake of argument, it's temperature and pH. And let's say that for temperature, you went from 0 to 100 C. And let's say for pH, you're willing to look at 0 to 14. All right. You take the best of those 5 first random experiments, and you're going to make that center, that will be the center of a reduced experimental space that is a subset of what you've already been working with. But you want to reduce that space. So instead of it being 100 degrees wide, that new subset experimental space is only 50 degrees wide now. And instead of looking from 0 to 14, you're now going to only look at something that's 7 pH units, 25 degrees to, let's say, one side, 25 degrees to the other, right? That gives you a total of 50 wide. And it's got 3.5 pH units high, wide in one direction, and 3.5 pH units in the other direction. You've reduced where you are looking because you got a better result. And you keep doing this, okay? In that new, smaller experimental space, you start it over. You run 5 new random experiments. You do not keep the old one that it was centered on. And again, you say, okay, I'm going to take the best of those. I'm going to center that into another subset experimental space, which is now half the size again. So you're looking at something that's only this is that exacting you're going to have to be to find it. You don't want to jump over it. I'm not very big on this technique because, again, you're running a lot of experiments to potentially get you just one that is better. However, if this works for you, it definitely works. It's just that you may have to cut it short. Again, you're going to run out of time, money, permission, whatever it is. All right, so this is going to bring us now to simplex optimization. I love simplex optimization. I have used this throughout my career, starting in graduate school. This works, all right? And it's very easy to do. It's what's called self-directing evolution of operations, all right? It will direct you toward the optimum, not just create a bunch of random experiments and use. And it tends to out every time you run a new experiment, it is better than what you've run before. Now, there are exceptions to this. I'm going to say that this is true about 80–85% of the time, which is great because this means you can stop it at any time. If you're doing this simplex optimization and you're merrily going along and you thought you had time to run, I don't know, 15 experiments, but suddenly something comes up and you're only allowed enough time to run 10 or maybe even 5, great. You have improved where you started from. It may not be the optimum, but you are better than where you were when you started. This is also, while you can stop at any time, it's open-ended. You can keep doing this for a very long time, but the changes in your variables become impossible to make. They're too small, and maybe the differences that you're starting to see in your results are too small as to be meaningless. You know, is there really a difference, and we'll use yield as an example, between 93.5% and 94%? Probably not, although if it's on a large enough scale, like a commodity chemical, yeah, that could be important, so it's worth continuing on. The calculations, unlike statistically designed experiments, you can do it by hand, you can do it in a spreadsheet. If you're really good, you can do it all in your head. All right. I typically use a form that's really a spreadsheet so that each experiment is on its own sheet or form. And it's easier for me to keep track of what's going on when I do that. If I have to go back and I maybe want to change something, do I have the information that I need? There are all sorts of variations to this. This technique goes back, I want to say, into the 1960s. It was originally developed for optimizing differential equation results where there's no unique solution. And how do you get to something? Since that time, it's been adapted to all sorts of things. But you can, for example, if your optimum is on the border of your experimental space, that is sometimes very hard to find with statistically designed experiments. For something like a simplex optimization, there are certain variations of it that let you find that. And by variations, it's not even so much the arithmetic, it's more the rules that you use as you move throughout this thing. You can use this if there are multiple optima. If there is, say, only one global optimum, you don't want to get stuck on a local optimum. Or maybe there are multiple optima that are really all equal, and that's fine. That'll let you find that. This is something I'll come back to, that you can either run each successive experiment one at a time as they're generated, or you can generate a small number of experiments and run them in a group. And there's a reason you might actually want to do that. It's a little bit more, I don't want to say scattershot, but it's, I guess that may be a good term. It's like a shotgun. Yes, you're aiming it where you want to, but then you've got pellets going outside of that ideal spot. And this can be used in the plant. Again, I emphasize your experimental space, but if you're in a position where you have to make saleable product every time, you can use this technique. It may take a little longer to get to the optimum, but you can do this. All right, so what is this? What is a simplex? So if you have, say, a single variable, right, you can do a simplex optimization on it. In fact, it's a special type called uniplex instead of simplex. Well, you have a point, right? It's one variable. So add one more, that's 2 points. So that's a line segment. Okay. With two variables, like we've been predominantly looking at, the simplex is a triangle. If you have 3 variables, it's a tetrahedron. More than 3 variables, the nomenclature for what these figures would look like, they're called polytopes. So if you have a 6-sided figure, or a figure in 6 dimensions, that's called a polytope of 6. I wouldn't know what that looks like. I have a hard enough time with seeing things that are in 4 dimensions. They look really strange to me. But that's what a simplex is. So let's look at an example. This is a fixed size simplex. Let's say, for the sake of argument, that you're starting down here and you've used your chemical intelligence and you do not know, like, how to get from there to the optimum, which is the center of this oval. All right. So you're going to do this maybe in a laboratory, maybe in a plant. In a plant, this is considered the step size. Okay. In a plant, you use a small step size, because if you use a large one, you might make something that is not saleable or has to be blended off or has to be reworked or reprocessed. So this is what's called our initial simplex. And I'm not going to get involved with the math here of how, if this is where you're starting, how you choose these 2 points, but suffices to say, here's our starting simplex, a triangle. What is done is mathematically, you take the worst point, your worst result, which is this one, and you reflect that through the line determined by the 2 remaining results. That generates this point here. You then get rid of this worst point, and now your simplex are these 3 results. You do the same thing. You take the worst one, you reflect it, gives you this point. Get rid of this one. You'll notice every time we've run, it has improved. All right. Even though we're not headed directly to the optimum. And we keep doing this. We get rid of this point, it's reflected, this point, so forth. Finally, we get to something where a different point is now being reflected. This is now your worst point. Here we reflected, okay, the new point isn't as good as one of the retained points. So we get rid of this other retained point, reflect it. We keep doing this and we keep going. And in a perfect world, what will happen is you will either get to the exact optimum or slightly off because of the step size, right? And it will process about this point. Maybe this point is over here. Maybe this point is over here, but it'll start to precess. And that's how you know you've gone as far as you can go. But let's say that someone said stop and you're at this point. Well, congratulations. You're here and you started here. You have improved this. And at that point, you might be able to make a case for, hey, I got this far. If you give me some more time, resources, money, I can get even better. All right. So here's another type. And oh, I said I was going to do examples. Let me back up. So like I said, I sort of discovered this. I found out about this in graduate school. And my particular thesis project involved using a particular reactant. And that was it. There was no guidance as far as what to do with this reactant. So I had my breakthrough experiment, something that they apparently had been trying to do for some time. I was able to do it. But the first time I ran it, I got about a 70% yield. And I didn't want to go to the trouble of having to purify it and other stuff, having to deal with it. So I looked at just two variables. It was temperature and concentration. So I ran this simplex. I was in graduate school. While I didn't have an infinite amount of time, I was able to do a lot of experiments. And using a fixed size simplex, and remember, I have no idea what the response surface looks like. I ran the yield up to just under 95%. Now my advisor was very happy. And I was able to then start exploring different substrates, so forth and so on. But I had conditions that after the fact, I was able to rationalize. The breakthrough experiment was basically proof of concept. But as it improved, I said, yes, this makes total sense. All right. That was fixed size. Well, what about variable size? This is something that you would probably not want to do in a plant because at times you'll be making big jumps. And it proceeds off of the slogan that if a little was good, more is better. All right. So here is our initial simplex again. Okay. We reflected the point and it was good. So mathematically, you do the equivalent of doubling that distance, and that brings you here. So you made a big jump now. You went from that initial simplex to something that's further out, but the triangle that it made is stretched out. And you'd still do the same kind of thing. You take the worst point and you reflect it. I'm sure someone tried to point out here it wasn't as good, and you keep doing this. Now, what will happen is as you get to the optimum, that simplex will shrink down, which is great because it lets you pinpoint where the optimum really is, as opposed to the fixed size where you're locked into that step size. Now you can go all over the place. Another example of using this, I started my career for a few years. Beginning of my career, I was 5 years at DuPont, and two colleagues of mine were working on, it was a fluorine-containing compound. I can't remember if it was a Freon alternative or a stain resist. It doesn't matter. Whatever it was, they knew that this thing could be improved because I think they hit it once, but they were never able to do it again. Now, at DuPont, the way it worked was, at least in chemicals and pigments, was that every chemist had a technician reporting to them. The chemists were not allowed, I shouldn't say not allowed, it was very frowned upon to work in the laboratory. That's what your technician was for. They wanted the chemist to sit there and have great thoughts and then tell the technicians what to do. Well, these two colleagues of mine, each one had a technician, and they ran a statistically designed set of experiments but they also incorporated, unbeknownst to the technicians, the difference between the technicians, so A and B. The result of that was that they still couldn't find this optimum. It seemed kind of flat to them, but the best news of all is that there was no difference in the technicians, how they were carrying out the experiments, because if there was, it would create a whole other level of problem. So at this point, they came to me and they said, we can't find anything. It's like everything we run gives the same poor result, but someone, somewhere, sometime had gotten a really good result. So I suggested that they use this variable size simplex. And what they found was that the optimum was a narrow ridge that they kept jumping over because in the statistically designed experiments, they just never happened to hit it. So now they were all excited. They got what they wanted. And one of the fellows there did something that I had not thought of before, and that is he graphed the surface that the simplices explored. So he ended up getting a response surface map, but it was a ribbon that got progressively more narrow. But you could see it was level, it dipped down a little bit, maybe dipped up a little bit, and then it shot up to this ridge. So while you'll never really know what the response surface looks like, you can at least get a tiny idea of a sliver of it. That is the variable size simplex. So let me talk about some variations or how you might run a variable size simplex. Big starting simplex. The reason for that is when you're doing variable size simplex optimization, one of the things it can do, and I showed you that on the previous slide, is contract. So if you start out with a really big simplex, any reflection is going to carry you outside your experimental space, which is fine because then it will cause you to pull it back in. So here's an example, right? You have this wonderful experimental space. You run a big simplex, reflect any of these points here, and you're outside of your experimental space. So it pulls you back in. All right. Here's your new point. You can run this. From the way this looks is some other point, probably this one, was still needed to be reflected and was carrying the experiment outside the experimental space. So it contracted again. And this will keep on going. Sometimes it does, sometimes it doesn't until you get to the middle. Now, another success story with this. So when I was at Johnson Matthey Pharmaceutical Materials, there was a process engineer who was responsible for running a particular process or a set of processes to lead to a particular active pharmaceutical ingredient. And one of the steps that he was running, it just wasn't working as well as really everybody needed it to be. But the information that was in the reports, which was well before my time, didn't really help him. So I said, all right, you're working in like a 10-gallon scale. Why don't we do this? Who cares as long as it's safe? Who cares if it doesn't work? It's a very small amount of material. We'll just dispose of it, but at least you'll get someplace fairly quickly as opposed to a small fixed size simplex. I said, great. And I think the two variables were something like temperature and pH. I know one of them was pH. Well, the process was being run on the basic side. For whatever reason, I never got all the details. Well, because I had told him big starting simplex, be bold, right? Fortune favors the bold. So he ran a very large size one. He did these 3 experiments. One of those experiments was in the area that made it acidic. And lo and behold, it started to work perfectly. So he never actually carried out the simplex optimization. He just ran 3 experiments that could have been used for doing a simplex optimization, but one of them was already so good, stop the simplex. You don't even have to do it. And he was there. So these things really do work. And eventually that process got scaled up and everything was great. So again, make sure you're safe in your experimental space, but be bold within it. I alluded earlier to getting a group of new points when you do this. That's called multiple move simplex. That comes into effect when you have one of 2 situations. If running the experiments or the process or whatever it might be takes more time than the analysis of the results, then you do one new point at a time, like we've been talking about. If, however, the analysis takes longer than it takes to do the experiments, then what you want to do is run a bunch of experiments, hand it off to analytical or analyze it yourself, and then take all those results and use them. It's, like I said, a little bit like a shotgun. While you're aiming for what you hope is the optimum, one of those other pellets, so to speak, one of those other experiments may actually be closer to the optimum. And while I haven't done that, I do know people that have, and they've been very successful with it. Finally, you do not want to get bogged down in the arithmetic for this. It's really very simple. Instead of reflecting it, say, which gives you a straight line, some people fit it to a second order equation. I don't think that's worth the effort. It's good enough. Believe me, you will get there. So these are the references that I'd been using. The one from Hendricks is the one that discussed a lot of the random methods that you can use. The article by Carlson was the one that talked about the order of addition. And then finally, you have here a book. It's basically the Bible of simplex optimization. Very easy to read, great examples. I mean, if you're 13 years old, after reading this book, you can do it. The problem is that that book is out of print. So in addition to, I guess, getting a copy or having a copy of this presentation available, please feel free to contact me. This is the Chemical Consultants Network, and I can help you out or do the work for you. So just in summary, we've talked about what is an optimum, how to quantify it, things that can help you do order of addition, probability that you're going to improve things, using random experiments to improve things, and finally, simplex. And I want to point out just one last thing. The major author for the simplex book is not the first author. The major author is a fellow whose name is Deming. And anybody who has been in the field of either continuous improvement or optimization might recognize that name. This fellow's name is Stan Deming. Edwards Deming, just after World War II, was sent over to Japan to get them started on continuous improvement because it was not well received in the United States. So he went there and he pioneered a lot of statistical process control, things like this. So I had the opportunity to meet Stan Deming was at a lecture, and I said, "Hey, by the way, are you related in any way to Edwards Deming?" And he says, "I get that question all the time." He says, "If you go back to the 1700s, they have a relative in common." So I guess they have a gene for something about improvement and optimization. Well, thank you very much for listening to me. There we go. I wasn't able to see your comments while I was doing this, unfortunately, because I had to start it and stop it as my server quit. But if there are any questions, I am more than happy to answer them. I just suggest that we do it verbally. Now, the real question is, how do I choose a person? Let's see, I don't have, oh, wait, here we go. Let's try this. Okay, I think.
You've got a question from Joe Martino.
It's not showing up in my chat, but okay.
All right, I'll read it to you. It says,
Okay.
for your initial 4 experiments, would you need to randomize the order of experiments to minimize potential bias once you have the permutations initially set? Same question applies
Yeah.
for iterations you derive.
Right. No, you don't have to randomize them. You're starting with the best that you know, and then you're breaking them apart, the pairs one at a time. So if there's an intermediate that has to do this, you'll find it, or at least you'll destroy it and then remake it. Oh, there it is. Stan Deming, yeah, teaches. Oh, he does. That's interesting that Stan teaches DOE for ACS. The guy is brilliant. I mean, he knows how to explain stuff. Okay, now I think I can see your comments.
Paul, in the simplex method, you mentioned the triangles that it was all set size triangles, and then you went to the triangles where you had various sizes. How do you choose the sizes of the reflection?
When it's fixed size, it's just a mathematical
Right.
reflection. When it's variable size, it's the method tells you how to do that. Basically, what you do is you do a normal, happy, easy reflection, and then the method, you do a little bit more arithmetic, and that tells you, is it expand, if it's good, is it expanding? Do you need to contract it? There are 3 possibilities. One is that you expand, your new result was better than your previous result, so you want to expand on that a lot. Another possibility is that your result is better, but not as good as something that would require you to expand it a lot. So that's a type 1, I guess, contraction. So that makes your new point between the best old point and that giant reflection. The contraction, I guess, type 2 is when it pulls your reflected point is so bad that you don't even want to extend it at all. It pulls it back inside the original simplex.
Wow.
Again, it's the arithmetic behind it. It's really simple. It takes me longer to explain it than it would to do it in your head, which is why I'm very big on this technique.
Good, good.
Okay. Yes, it's
Are there
good
any
to
other
see.
questions?
Hello, Paul.
Yeah.
This is Rado. We all know that the optimization is fundamentally important in terms of like processes. My question is, would it be possible if we focus on the specificity by discretizing and scattering the variables, and that might actually resolve the 23rd problem of Hilbert? I have issues now because I've been working on biological chemistry mainly, and because there are so many variables there due to the
Right,
transformation,
right,
all these
right,
constraints.
right.
And now there is a focus, it kind of like not focus, but like a specificity on like in chemistry, we do tend to compute and this physical variable of pH. What we have discovered within the past 20 years is this variable called the pK, which is the partial compression of carbon, which is the metal groups, which just basically jump from a place to place, and we don't know what they're actually doing, but they're involved with this regulation. So I was thinking about whether it would be possible optimization and total simulation, because now we can kind of guide tissues, make cells out of nothing. 20 years ago, that was a dream. I would assume that 20 years from now, we would be able to make organs even, and we wouldn't need transplantation. We wouldn't need any of like this stuff. But that's more like advanced medicine, well, because chemistry is so spread out and its involvement in different disciplines, and it requires a cohesion. I have to say that I did enjoy your lecture, and
Oh, thank you.
because I'm more focused on to the bio-inspired aspect of natural synthesis, which is mostly simulating
Right.
similar
Well,
to
one of the
aldol in
things,
an inner reaction. But yeah.
Right. One of the things, I mean, the best way to use simplex optimization, as much as I hate to admit it, is you start out by using statistically designed experiments, but a screening design.
Do
And
you
that way,
actually? I'm sorry for interrupting you, but
no,
you
please go
do
ahead.
need the nucleation centers, because you wouldn't like to run in a complete like randomness. It's good to begin with
Right,
a
exactly.
random, yeah, because you can have a multiple sources of randomness, and in that way you could eliminate
Exactly.
action. Right.
Exactly. So this way, you'd run a screening design, you find out what your important variables are,
Right. So you
then,
can eliminate the
right,
ones that doesn't matter quickly,
exactly. And
or
then,
they don't mess
right,
up within the further processes because it's
right,
difficult.
exactly. Then there are two things you can do. You can either run a simplex based on that, or you continue with the statistically designed experiments, but now you're into response surface mapping or developing the equation that
Right, that's the functional density theory
shows it right.
technically.
And then you use simplex optimization to zoom in on the best, the best
So,
result, the real
so that would be the
optimum.
specificity technically.
Exactly. So there are ways you can do this. Probably the only thing that both techniques, simplex and design of experiments, doesn't handle well are non-quantifiable variables. So, for example, if you're looking at different catalysts, but you're not using some property of the catalysts to quantify them.
Well, that's
Or
exactly
like
what
in
we are working on now, Paul, because in biology
yeah,
we call these pieces enzymes, and they transform and they change all the time. So they
there you go. Yeah,
dimerize
that
and then they yeah,
right.
it's
Perfect
different
example. In
story a little bit.
fact, that's where the example that I gave you of two of my colleagues at DuPont, you cannot like go on a gradation from one technician to the other, right? It's either all one or all the other. There's no such thing as a quarter of this technician and three-quarters of the other. That doesn't exist. And that's always been a problem with a lot of these techniques, that you just have to kind of bite the bullet, pick one, go through some of this stuff, pick another. Hopefully, as you're doing this, you are learning enough to give you some insight as to what might make a good enzyme, a good catalyst.
So
It's
you technically
hard.
try to extract properties in a way.
Right. That would be right. If you could do that, that's the best possible situation. Like for a catalyst, it might be the size of the reactive site on the surface of the catalyst. At some point, you're trying to get to something that you can quantify, but if you can't, you just have to bite the bullet and try each one. I hope that answered your question.
It did in a way. Well, thank you, Paul.
Okay.
Well, that's very informative. I really appreciate this. This was a excellent presentation. Thank you very much, Paul.
Well, thank you.
And
I guess I should join. I guess I should join, huh?
we'd love to have you back. Yeah. Yeah. Before you go, are there any other questions? All right. Well, thank you very much. And please, not only do you want to join, but you also may want to run for a leadership position in this organization. You, Paul, and everybody else who's listening. Thank you very much, and goodbye.
Okay. Bye-bye.
Bye.